Thanks a lot, and thanks all for joining me today to talk about DrawMeATree. This is a tool that I've created now 1 year ago, and that completely changed the way I do reverse engineering. So my goal for today is to talk with you about how it got created, why, and for what purposes, so to see if it can change the way you do reverse engineer too. Before we get started, a few words on myself. So I work as a security researcher, but I like also to deep dive into undocumented features or things that are little understood in the community to share them during blog posts, conferences, workshops. So super grateful to be here today. And when I don't do that, I like to bake a lot, mostly because I love eating. Enough about me. Let's get started. Let's take a step back and go where it all started. And initially, we need to understand why tooling matters. So at the beginning of my career, not that it's been a very long time ago, but you got the point, my mentor told me the following. He told me, a good reverse engineer can reverse an entire binary to get their answers, but what makes a great reverse engineer is that they reverse exactly what they need to get theirs. And initially, I didn't really understand because, well, being able to reverse an entire binary sounded great and certainly good enough. But with time, you realize that, sure, you can reverse an entire binary, but you're going to spend your nights doing that. And sometimes it's great, but sometimes you can put this energy and this time into something else. So with time and nights, I understood that the time efficiency matters, especially in reverse engineering. So I was left with an even bigger question of, great, I know I don't need to reverse an entire binary, but how do I know what I should or should not be reversing? And I was this very confused reverse engineer looking at a fortress, because that was really the system with closed doors that is still running in front of your own two eyes. And even if you don't know really quite yet, well, the answers are there. The component that you're trying to understand is fully running and fully independent and doesn't need you to run, which means that there's something inside that explains how it works. And your goal is just to find it. But you probably don't want to explore every room of the fortress when you're searching for a treasure. You don't want to go from the dungeon to every tower, to every room. You want to know where to start and try to do it in the more efficient way possible. And also another challenge when you look at this fortress is, how in the world am I going to get in? So that's what reverse engineering is about to me, and that's the beauty of it. This is about the journey to explore the fortress, to understand how to access it, and how to access the information to find your treasures. So now that we know what we're going for, let's summarize what we need. The most important thing is to identify your treasure. You cannot start a reverse engineering protocol if you don't know what you're searching for, because knowing what you're searching for will impact what you do and how you do it. If in your fortress you're searching for an endangered princess, maybe you will start with the dungeon, maybe not. If you're searching for a big chest, maybe you'll start in the guarded tower. It's all about the approach that you'll need to start your reverse engineering procedure. You also need an overview of what you're going for in the fortress. I'm not talking about a full map. I'm talking about knowing what to expect. In reverse engineering, if you're searching to understand a new network protocol, you'll have this network approach and see how the component communicates, all of it. In reverse engineering, that will be the thing that determines what you're going for. And finally, you need a tool to actually break in, whether it's the fortress of the component. In reverse engineering, the tool is the way you access and interact with the information. So great, now we understood why tooling matters. So how do we find the good one? Well, if we had a Christmas list, I would say we need a light setup, because we're spending already so much time interacting with our tool, trying to deep dive into the fortress, that we don't really want to spend hours setting it up. So we want a light setup. We also want it to be user-friendly, because if we're spending nights on something, we might as well, make it easy. We also need it to provide information relevant to your needs. Sometimes you'll get an information about, the network, how it works. But if it's not what you're going for, well, great, but doesn't help. So it does matter what type of information you're getting to answer your own questions. And finally, that's what we were talking about. It's getting the more information in the minimum amount of time to build this efficiency that we were talking about and that will spare your nights. So we looked out there and we found some of the live monitoring tool, Process Monitor, API Monitor, Wireshark. For most of them, the setup is great. It's just a binary, you install it, nice UI, user-friendly, all good. But providing the information relevant to your needs, well, let's get back to our network example. If you're trying to understand how a component writes its database, well, Wireshark is not going to help you much. Sometimes with API Monitor, you'll get to see the calls, the APIs that are being used, but you won't see, you need to already know in advance to monitor them, to filter them. So if you already need to know what to monitor, sometimes to start, that's not the way to go, and so on and so forth. So they could be great for some cases, but not to break into a fortress to me. So we kept going. What about disassembler, decompiler, IDA, and Ghidra, and all that? So light setup, we're still good, because still a binary to install. It's user-friendly. Well, don't kill me quite yet. I think it's great. The UI is great. You get to interact with it. There are documentation out there that you can help and that can help you. Providing information relevant to your needs, well, it's the same problem. Let's say you try to understand an undocumented library on Windows. You open it, and bam, 500, thousands of functions. And the information is somewhere in there, but you don't really want to reverse those 500, thousands of functions. So information relevant to your needs, well, depends. Similarly, you'll see sometimes API calls with arguments, A1, create file, A1s. Great, what is the file being opened? And if you're lucky, there will be a hard-coded path somewhere, but sometimes not. So this won't always give you the information you're searching for. And the more information in the minimum amount of time, well, definitely not, because that's where those disassembler giving you the full picture cannot answer in a very short amount of time, because you'll need to dig in, and if you're lucky, you'll find it soon, but you can't really rely on luck for that. So that wasn't answering our need either here. So we kept going. What about dynamic binary instrumentation tools like Intel Pin or all of the wrappers around it like TinyTracer? Light setup, well, I have spent some time trying to set them up, so I hope you'll be luckier than me, but to me they're not that easy to set up because you usually need many layers of the tracing, so Intel Pin, which is going to be your core pillar, and for TinyTracer, for instance, it's a wrapper around it that needs to compile everything to set it up. So not super easy to do. In terms of user-friendly, it's pretty much the same. Talking about TinyTracer here, it will give you a full list of all the function calls being made, but it will be this very raw data that you'll need to dig in, and that won't be nothing you can really interact with besides Control F. So it can be a bit hard to dig into it. Providing information relevant to your needs, well, they do, because they show you what is happening live on your system. So if you try to understand how a component works, it's going to show you all of the APIs that are being called. You can, unlike IDA, set up something to see the arguments. So if there's a create file call, well, you will be able to see which file is being opened. So it does provide information relevant to your needs, but that's the last point. It usually takes quite some time, not only for the setup, but to get it working, to be able to interact with it, to have your information. So we were getting closer, but that wasn't quite it yet. So we kept going. What about debuggers? WinDbg, x64DBG, AllDbg. Light setup, we're still good. Still a binary to install, so fair enough. User-friendly, well, again, it depends. Some people are very comfortable with debuggers, which is great, but sometimes it can be a bit hard to start. For WinDbg, for instance, we were doing a workshop yesterday, and I realized how confusing it can all be when you start with a debugger and you don't know any of the commands, and you have to get to know them to interact with the debugger. So that's a pretty tough effort to do initially, and once you have it, great, works pretty easily, but it takes some time, so it's a middle ground. Provide information relevant to your needs, similarly to what we were just saying. It will, because it shows you what happens live, so you can display arguments, understand every API or function calls. This is this dynamic vision that helps understanding what happens under the hood. But the more information in the minimum amount of time is, again, here the problem. Because you will get to see all of the API and all of the function calls, but you need, for instance, on WinDbg, to press P, 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 to go next, 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 through every instruction or every call. And it can take quite some time too. So we were out of ideas, and we were like, okay, well, some tools partially answer to what we need. And when we look at the summary of those tools, we thought, well, maybe we can do something about the user-friendly part. Because, user-friendly, it's all about the UI and how you visualize and access the information. So maybe we can do something about it. And what about the more information in the minimum amount of time? Well, maybe we can too. If we could find a way to select the information that is relevant and find a way to display it in a better format, maybe we would have a way to do that. So we looked, and in WinDbg, we found this amazing command that's called WT that will execute from a breakpoint through the entire function until the function returns. This means that from the main of a function, you will get to see all of the calls that are being made. And it may be a bit hard to see initially on the screen, but basically what this capture here shows is that we start from the main of the binary curl, then we call memset on the second line here, that is at the depth level of 1, that's the number indicated here. Then we go back to the main, then we call whatever function this is in UCRT base. Then we go back to main called win32init, and that's what you see on the right of the screen. That's the function flows showing you what happens in which order from the main until the end of the main. And we were like, oh, well, this command, has all of the information because it shows us this live vision, this dynamic approach of what's going on right now. And since we know what's going on, if we want to display argument, well, we can just, put a breakpoint and go straight to it, display your argument, and interact with it. So we had this feeling that the answer was here. But the problem with WT, and we'll take an example to illustrate that, is that it can get quite heavy quite easily. So if you're not familiar with the SC binary, this is a native Windows binary that allows you to query information about a service. So the spooler is our good old friend, the printer. And if you do SC query spooler, it will show you a few information about the service. So is it running? Is it set up to start at boot? And informations like that. And I wanted to know how does SC find this information about the printer. So I thought to myself, okay, let's try with WT. Let's see what WT shows us of what happens from the main of SC to the end of the main, because somewhere in the bit in between, that's where the information is being found. So I run WT, and looks great. That's exactly what I was expecting. I didn't triage the depth, because you have this optional argument to stop to go into the deep at some point. So those are the layers that are optional in the command. And I waited. And when I looked at the result was 23,000 of lines. 23,000. I certainly didn't have the time for main to go through every line to understand what was happening. And yet, the information was here. WT knew what was going on. So we thought, okay, well, WT has the information. What if we could visualize it? What if another format would help in understanding what's going on and instead of reading through it, being able to see it? So we created this tool called DrawMeATree to do just that. DrawMeATree, so is a Python tool that will convert this output that you just saw, those 23,000 of lines, into a visual tree that will allow you to see in just one picture everything that's happening. The tool produces two versions. You have a full tree that will show you all of the calls that are being made, but you'll also have a filtered tree. And that's the real value of the tool, being able to filter out all of the functions that do not matter for you, so all of the allocation routines, all of the free, all of the close handles, opening handles, and sometimes those functions will matter. but it all depends on your questions. So that's what we were saying initially of think about your question, think about what you're trying to answer, and using DrawMeATree, you will be able to filter out all of the things that do not matter and remove duplicates. And at the end, you'll have this clearer picture of what's going on because you'll be able to triage what matters and what doesn't. So it's very useful, including to identify components, because the tree shows you each model based on colors. So each model will have a color. So looking at the tree, you'll be able to see which models are being involved, which model is calling which other model. You'll get to see functionalities based on the name of the APIs and things like that. You'll see this overall flow of, what is the first step what is the first step where main goes, or whichever function you're seeing. And this whole thing will allow you to summarize the information. So if we go back to how the tool looks like, this is the interface. The only thing that is mandatory is this Python script, so Python and the name of the script, and the argument that contains the logs containing the output of WT. So you go from your WinDbg's session, where you display all of the logs, you send them into DrawMeATree, and all of the rest is optional, because we really wanted this tool to give you this filtered version with the default, first process, and being able to give you the options to customize it, but not mandatory. So here you can see the optional arguments. The depth level, this is an additional way to filter out how deep you want to go within the tree. So if you want to see, 5 functions under or 3 functions under, and so on and so forth. You'll have all of the filter words. So those ones here are the default defined one, but you can customize it to adjust and fit your needs to answer your own questions. You can also print it in the terminal as you're generating the trees. You can, and that was a request from my manager, to show a different direction, because some people want to visualize it from left to right or from top to bottom. By default, this is left to right, and where the results are being exported, and also how the process is going. So if we go back to our example with SC query spoiler and our 23,000 of lines, if you remember, the tree generated looks like this. You have 1 color per module. So you begin with SC, the binary that we started from, the W main, that called a worker at some point, that called all of these modules here, the SEC host, and then under the hood RPC air. And looking at the picture, you can identify which components are being involved with this module, SEC host, and you can also see that it does use ALPC. And with just 5 minutes of processing time, you generated the logs and you filtered it out. You can already get information. You already get this overview of the fortress that we needed. You also get to see the global operation flow of, okay, the main at some point is going to call this subfunction called worker that does, opening a handle. And then we open SC manager, and then open service and query status. And you also see where you need to deep dive. Here, if we wanted to see how it works under the hood, we would be able to put a breakpoint into query service status and deep dive into this RPC or all of the ALPC a bit above. Because it's hard to know where to start if you remember our fortress. And it is all about showing us the way, showing us an approach and one of the doors that can be explored to get your answers. So when we go back also to our wish list, let's see if it fits the criteria. Well, the setup is pretty light because what you need is WinDbg, Python, and the dependencies of Python. So I think it's pretty fair. User-friendly, well, this is an interactive command line that you don't really need to do much about. You saw that we could just use 2 arguments and we were already having a result. And you can add your custom filters if you want. We also wanted a very nice result to have. So this graphic tree to me is a nice way of visualizing the information. Providing information relevant to your need. Well, It's similar to the debuggers and the dynamic binary instrumentation tools that we had that were showing us live what was happening to answer, the question, how does the component works? So to me, it does provide this general flow, the actors, the connections between functionalities. So that was relevant to the needs. And the more information in a minimum amount of time, well, that was the entire point of WT, of needing only the time to execute WT and then filtering, and that's it. And now you know where to start. You have this access into the fortress that we were talking about. Some limits that are still worth to keep in mind, because no tool is perfect, and this one either. The chronological order is not being guaranteed. Because we're using trees, it means we have this criteria of staying visually organized. So sometimes, if you have function A and function B calling function 1, if it makes more sense to display those functions in closer, well, the dependency that generates the tree will do so. So when you see function A, you cannot know for sure that this function A has been called before function B. So that's something to keep in mind. Also, the Windows default image viewer sometimes is a bit slow to load. So depending on how heavy is your tree, you might need to use an alternative software. There are plenty of them. It's not a problem, but it's still something to mention. And the dependency that the tool is using, called dot, limits the number of lines that they can process to, I think, around 80,000. I've been limited, to be honest, only one time, but it is still a limit that is worth keeping in mind. So the methodology would be the following. You need to generate the logs with WT through WinDbg. To do that, you can either copy-paste the logs directly, or you can use the command .logopen that will trace your debugging session, and you will get directly your logs into it. Then you try to identify the maximum depth that you need within your trees, because since you can cut it out, this will be one of the ways to make it, summarize the information and get rid of the depth that you don't need. Then you will try to identify all of the high-level nodes that will be irrelevant to your needs. Again, we're trying to keep in mind the questions that we're trying to answer. And if the first thing that a function does is allocation routine, well, you can filter out this allocation routine function because you'll get rid of all of the subcalls that are in this function and that won't answer your questions. And once you've done that, well, you can remove some of the smaller nodes to make the picture appear with only what matters to your need. And I think that's a time for a demo. Let's take another example of a native Windows binary with who am I? So who am I, for those who are unfamiliar with it, is a command line that gives you the name of the user. And my question was, hey, how does who am I get the information? So let's open our WinDbg. Let's start a session. We don't need that. Let's put the breakpoint at the beginning. We go through there. Let me zoom in a bit. Okay, we're at the start of who am I. Let's clear the screen. Let's use WT and let's filter out to, let's say, level 5. We're choosing here the level 5 because we don't really need usually to go really deep to understand the high movement and the high flow of operation. So as we can see, it does take quite some time. Let's prepare the file to receive the logs. Okay. And when you open the tool, so this is on a GitHub, you'll get both some of the embedded examples if you want to practice. You'll get the script, DrawMeATree. You'll get those two output, so the full version of the tree that contains all of the function calls that got processed within the wherever you put your breakpoint. And you get also this filter tree that is the real output you'll be interested in. Okay, so we copy and paste the results. And how many lines do we have? Okay, fair number, fair number. Let's save that. Who am I? So now let's try to open it. Oh, I might have missed the extension. Let's put a txt file. Okay, I don't think I'm in the right directory. Great. So we'll launch the script, Python, DrawMeATree. Let's zoom a bit. And then we just need the log file. So who am I? Syncon. The interface will guide you through the steps of telling you what is being processed at the time and show you at which step it is. So, first parsing the output, then creating the trees, generating the output, and confirming where the trees have been generated. So let's look at the full tree. The full tree is usually very scary because it has a lot of function calls. And the usual reaction I'm getting is, hey, this doesn't sound better than 23,000 of lines, but that you gotta start somewhere. And the filter tree won't be much better because this is the initial version we have. And now we need to work on this one to create our own tree to answer our needs. So let's try to see if we can get rid of some depth. When we look at the big picture, we can see that at some point in the execution, we have NTDLL calling more NTDLL functionalities. This is usually, not always, but usually a sign that it is calling sub-functions that are doing the same functionalities. So here, let's try to remember our questions. We're trying to answer, how does whoami binary gets the information about the user? So here we're looking at the function and we see, okay, NTDLL, compute lang goes to culture name. Well, it doesn't really answer our questions. And we can see a pattern of sub-functions repeating, which means we can at least probably get rid of one layer. And I think, if I'm not mistaken, that we had a filter on depth 5, which means we can add another filter to level 4. So let's go back to our tool. So depth level is the keyword to get the number that you want. And we can also try to identify those high nodes that by getting rid of a high node, we can get rid of the entire branch. So we start with whoami main, and let's see what it does. Whoami main calls process options. Okay, well, process options sounds like it's parsing the arguments of what we ask. In our case, we don't really have any argument that we're interested in, so we can probably filter it out. So we add this keyword A as an argument, and it's a string match, so you have to be mindful of what you're filtering. You have to be mindful of case. It is case sensitive, and you can filter out any function that will contain, you will filter out any function that contains the word you're putting here. So let's say you want to get rid of all of the MSVCRT, which is a library that usually doesn't do much of the functionality that you're interested in, but more string processing and allocation and all that. So if you add to your filter words MSVCRT, here we are not only going to get rid of this one, but we will get rid of all of the calls that have MSVCRT in their module names. So be mindful when you do your filtering to make sure that you're not getting rid of things that still matter to you. So here we said we could get rid of process options because it's not answering our questions. Let's see if there's any other big high nodes that we could get rid of. From the main, we can see it goes to WS user. Okay, what is WS user going for? Oh, for a free memory. Okay, well, it doesn't sound super relevant since it's the only one. So we can probably filter this one out too. WS user. Release global. So what is release global doing? So we follow the lines. There's one going to the dynamic array. Okay, not super interesting for us. Here another dynamic array, destroy dynamic array. So with one look, we understand that this function, release globals, will have something to do with how the results or whichever information it holds is being held and allocated because it's about the dynamic array. So we're not really interested in that because it doesn't answer our initial question of how does the information is being found, so we can filter it out. Any other high nodes maybe? Let's keep going. So WMain, going to display account name. Oh, that's a name that sounds interesting for what we're searching for. We might as well leave it. Let's keep going. WS access token, well, it goes to close handles, okay. Well, since we don't really see what else it does, maybe we can leave it here. It's okay, you also don't have to add all of your filters all at once. You know, it's a work that is supposed to be interactive. So let's start with those filters and see if we want to filter more after that. So it generates a new picture. Oh, and it does look a bit better already. So let's redo that again. WMain calling setThreadUI language. Well, we don't really need that either, so we can add this one. setThreadUI. You also don't need to put the entire name of the function since it's string matching. We're still with our init function here that does some more init. We're seeing some functions that do something that we don't really know, but that might be relevant, so let's leave it here. We can also take a deeper look on what happens under it. For instance, we can see, you know, get buffer size. Get buffer size is not going to help us, so we can filter smaller nodes now that we've gotten rid of all of the bigger ones. We still see some dynamic array, so we can, we can add the dynamic array one and the setThreadUI. Let's keep going. Close handle that we're seeing here doesn't really matter either. Close handle. Oh, we're seeing in our display account name a function called getAccountName. Well, that sounds like the place that we're searching for. Let's try to get a clearer picture before deep diving into that. String concatenation, well, we can probably get rid of that too. Concat. String lengths in byte, again, more string processing, so we can also get rid of that. We see also those functions that, again, don't really matter. But here we see they're being called from something called showMessage. Well, the function showMessage probably shows the message, so doesn't answer our question. How is the information being retrieved? So we can also filter it out. Show message, let's get rid of that. Let's regenerate, see how it looks. Let's go back to this. Let's open the results. Well, and now you have a picture that is already more clear. So if we take another look, so the main calls something that inits. Init does get information about tokens, okay. Oh, this one is copying a SID, okay, well, good to know. After that, it calls WS access token, well, free memory, that calls access free memory. Well, you know, this one is not relevant to us. Okay, then it calls display account name, that calls get account name. Oh, well, get account name sounds like the place where it's supposed to get the account name. So we'll look up on what it does, how it looks. Oh, and we see lookup account SID. And now that we could visualize what happens, and you know, after that we see all of the other functions called, but that do not really do anything related to the account name, we know that we have found the information. And we could keep going and keep going on clearing it until we have a very clear picture of it. But we don't even need to do that because, as you could see, we did find the information. But if we wanted to get a really, really clear picture, we could filter it out until this point, where you have only the functions that matter. And when you look at this very clear picture, you can see that you have the name of the library implementing the functionality you were searching for, scchost, and you can also, you know, double check your assumption. That's what reverse engineering is about. It's putting the pieces of the puzzle together and checking what you just saw. Is what I'm thinking correct? Does that make sense? So we open scchost and read, you know, the file description. And it tells us, oh, LSA lookup API. well, LSA has to do with all of the account information. So that sounds great. Then we're looking at this bigger picture of, oh, look up account SID. Oh, maybe that's what matters here. So we go into the documentation, checking again our assumptions. And MSDN tells us, this function accepts as SID as an input to retrieve the name of the account. Well, here's part of our answer. This function gives us the account name, but we'll still don't really know how it got the SID, right? So we look up in the other part of the tree to try to find the other part of the answer. And we see, we have in this init phase something that says get token information. Well, let's take a look at this function. And MSDN tells you this function retrieves a specified type of information about access token. And it takes as an argument a class of information. And the tree won't show you exactly which class, but it tells you where to put the breakpoint, where to get this information. So next thing you do is you put a breakpoint in this function to display, well, the second argument that contains this information class. And then it tells you it's the value 1, and value 1 corresponds to token user structure, and the token user structure has a SID. And now you've put another part of the puzzle together. You know that the main called this function init that got through get token information, the SID, and with the SID enhanced, it went to the second function, get account name, and used this lookup account SID to get the account name. And here you go, you have your answer. And again, it took us, 10 minutes, maybe 15? And with that, we could see the overall flow, identify the components, identify where to deep dive, because we didn't have all of the info, and it's okay. What we wanted was this tool to break in through the fortress, to get the steps into it, so we could explore on our own, and without having to go through every instruction of the binary, we could know where to start, where to go, confirm our assumptions, and you got our answer. So to conclude, I'd like to go back on what my mentor told me. When he told me that a good reverse engineer could reverse an entire binary, sure, but that what makes a great one is that they reverse exactly what they need to. And I hope now you've understood that it does matter, time efficiency, and that this tool can get you this time efficiency that you need to be a great reverse engineer. For the reference, the tool is available on CrowdStrike GitHub at this address, and for the rest, I redirect you to the documentation. MSDN does a pretty good job with WT, and I hope you'll get to use it and change your way of reverse engineering too. Any question?
All right, I think let's give a round of applause for Mathilde. Okay, so let's open the floor for any questions. So if you have any question, please raise up your hand. Okay, at the back.
No photo. Don't take photo. And so, thank you very much for the presentation. I have a simple question.
Yeah.
What happens if you have the source code in min form, MIN, and as well as if you change the whole thing to the different base, like base 64 or Octa or whatever base that you choose? Can this be done like at a click? Thank you.
So if I understood correctly, you're asking what would happen if you have base 64 strings in base 64?
Quite a lot of times that people don't want you to read the code direct. Of course, if you have any other base than the normal base 10 ASCII format, it is very possible you can translate it quite fast, but without going through that kind of step. For example, like min.js. So how do you get this done as fast as you have demonstrated? Thank you.
Okay, so yeah, it's really common to have also, for instance, malware that use base 64 encoded payloads without their binary. And when you open them into IDA, usually you see this very big block of base 64 and you're like, I have no idea what it does. So the tool, what we need to really keep in mind is that it does this dynamic version of it. So the tool will see what the OS is seeing. So it won't see anything of the encoded base64 thing, it will see what it does. So if this base64 the string is calling nt create file, it will see this API call because that's what the system is doing. It is really monitoring what happens. So you will see all of the APIs being called by this defined code. What you won't see, though, is let's say you have, this defines an entire binary. This base64 is just an entire encoded .exe. If you don't have the symbols of this binary, and that the functions are being defined with, sub, 623A4, you will see just this name. You won't be able to have the function names because the function names are being defined through symbols. So without symbols, you won't have it. But what you will see is if this function with a really weird name does a create file, you will see this create file. Does that make sense?
Yeah, it makes sense. But what happens if you have mix, This thing happens when some source code, they like it in the way they want it, for some whatever reason.
What happens if they're mixed?
Yeah, that's both? Right. You have different kinds. The whole idea of the coder is because I don't want you to read it. Well, of course, you can read anything as if you want to, but I'm talking about parsing. Thank you.
So since it relies on what WinDbg sees, it will see what API calls are being processed by the OS. So it can be encrypted however they want. Whatever calls is actually happening onto the system. The system has to process it at some point. So the system will see what it processed. It won't see the name of the functions defined by whoever coded it, but it will see all of those create files because it has to process it somehow. So that's what WinDbg sees.